Friedman wrote a brilliant PhD on algebraic surfaces, and then he got interested in the core of algebraic geometry and how people got to the ideas and the way that it developed and how and why. And now he's a professor in the Cohn Institute for Philosophy and History of Science. So for me, it will be it was very interesting. I have his two beautiful books. To hear him here, maybe the first time that I hear him as a philosopher or historian of science. So you are on now.
Thank you. So first of all, thank you very much for the invitation, and I'm extremely sorry that I couldn't be here due to personal reasons, but well, Zoom enables us everything. And on a personal note, I have to thank Mina for supporting me and enabled my entire career, actually. So thank you very much. And without further ado, let's hear my talk about folding, which is pre-recorded, but obviously I will be here the entire time. So see you after the talk. Thank you very much.
About on the second problem, the duplication of the cube, I want to present shortly how the problem was presented in one of the accounts, particularly the account of theorem of Stern. When the God proclaimed to the delegates through the oracle that in order to get rid of a clay, they should construct an altar double that of the existing one, their craftsmen fell into great perplexity in their efforts to discover how a solid could be made the double of a single solid. They therefore went to ask Plato about it, and he replied that the oracle meant not that the god wanted an altar of double the size, but that he wished in setting them the test only it needs for their neglect of mathematics and their contempt of geometry. I will return later to this citation, but the problem is presented explicitly the following. Given the length of an edge of a cube, a second cube should be constructed having double the volume of the first. Or, if the edge of the first cube is of length 1, then its volume is 1 cube. That is also 1. The problem, hence, is to construct a cube whose volume is 2 times 1, which is 2, or to construct its edge, that is, a segment whose volume is the third root. However, if the edge of the first cube is not given, the problem is equivalent to constructing another segment such that the ratio between the segments is the third root. As already noted, the task of constructing these segments should be achieved only with straight edge and compass. Without any restriction on the instruments or mechanical devices used, this problem, as well as the other two problems presented above, were indeed solved already during the teaching. Obviously, I'm not going to speak about the history of these instruments or the solutions, but give enough to recall Plato's critique in an account of Plutarch, emphasizing the additional mechanical devices that were used to double the cube, in addition to the compass and the straight edge. Plato himself reproached several mathematicians for setting out to remove the problem of doubling the cube into the realm of instruments and mechanical devices, as if they were trying to find two mean proportionals, not by the limit of reason, but in whatever way would work. In this way, the advantage of geometry was dissipated and destroyed, since it slipped back into the realm of sense perception instead of soaring up and laying hold of the eternal and immaterial images in the presence of which God had always got. Well, if we ignore for a moment the passionate call at the end of the citation to abandon sense perception in order to reach the realm of God, it is essential to note another aspect, an aspect which is not at all present in the other citation. What is missing in every list of instruments were used and could be as relevant to their account is a substrate itself on which the various instruments, including the straight edge and the compass, were drawing, that is, paper, parchment, or papyrus. Let us therefore restrict ourselves to the three material mediums with which mathematical knowledge should be achieved, at least according to this count. The first two, which were explicitly highly favored, the straight edge and the compass, and the third medium, without which the act of drawing itself was not possible, the paper. As noted, the problem of the duplication of the cube is equivalent to constructing a segment of length per 2, given a segment of length. The question, however, remains open for centuries whether it is constructed from a straight edge and a compass. Only in 1837 it was proven by Pierre himself that if one constructs segments only with straight edge and compass, then constructing such a segment whose length is further root 2 is impossible. But in 1934, a paper called Some Applications of the Paper Folding Method was published by the Italian mathematician Margherita Piazzolla, proving that when one uses only a single piece of square paper whose edge is of length 1 and folds it, then one can in fact construct a segment of length 2, and this resulting from a single folding. However, Bellow's paper from 1934 was completely forgotten. This will be one of the central points of my talk. It was forgotten to such an extent that her method was presented in 1986 by Peter Messer, unknowingly that it was in fact Bellow's method, although formulated slightly differently. Messer depicts the following figure and writes the following. A paper square ABCD is divided into 3 strips of equal area by the parallel lines PQ and RS. The square is then folded so that C folds on AB and S folds on. Folding can be done, and it can be done only in one way. That is, there is only one way to perform this folding. Messer then asks to find the ratio of AC over C. Now, assuming that the length of CD is 1 and that one performs the fold according to how Messer instructs, the fold computation spent over less than 1 page shows that the length of AC is indeed the curve. Now, several questions arise. Why was the Bellow's method completely forgotten? How actually Bellow got this idea of using paper folding in order to construct a segment of length per 2? And why until 1918 no one has heard of Bellow's discoveries, which were which encounters with the Oriental community in Italy? The history of Bellow's discovery and its rediscovery is in fact a history of minor figures within the history of mathematics, but are hardly mentioned when one opens books on the history of geometry. It is this story that I would like to present today, and I will concentrate on 3 figures in my talk. Bellow and Uyas. I will start, therefore, analyzing Rao and how he folded a problem. Rao, an Indian mathematician, is perhaps the first mathematician who wrote an entire book on geometry based on folding. His book, Geometry Exercises in Paper Folding, published in 1893, Madras by the publication house Edison, was a unique book which attempted to base plain geometry, or at least the main construction of it, on paper. Not much is known on Rao's life. In the Indian Geographical Dictionary, published in 1915, the following entry can be found. So I'm not going to read all of it, but the last lines are important. That is the lines that actually lead to the publications. One is the exercise in paper folding, and the other, a later one, elementary solid geometry, which also tries in other ways to construct with folding elementary solids. Now, if we really concentrate on the first book, sequential exercises in folding, then this book presents various exercises and constructions using solely the means of paper. Rao indicates that in fact several constructions are easier to be done using the following. In paper folding, several important chromatographic processes can be effected much more easily than with a paper, with a pair of compasses and ruler, the only instruments the use of which is sanctioned in Euclidean drawing. In addition, referring explicitly to how pupils can use paper folding to learn geometry, Rao notes that folding would be helpful in the teaching of Euclid in schools and would give them, the pupils, neat and accurate figures and impress the truth of the propositions forcibly on their minds. It would not be necessary to take anything from trust. Hence, indicate that the pupil would not need to accept theories without any justification. Rather, it would be able to resort to manual and visual reasoning based on folding when dealing with geometry. The question arises, how developed was Rao's approach? To survey shortly the content of Rao's book, he constructs by means of folding several regular polygons and also deals with arithmetic series. More importantly, however, he shows how to construct conic sections by means of paper folding, that is, how to construct potentially infinite number of points on these curves. For example, and also in order to understand Rao's influence, it is essential to notice that Rao explicates the connection between folding and outlining a parabola, a connection which was noted by Rao for the first time. To present his construction explicitly, let us take a line A and a point B, not both drawn on a piece of paper. Rao notes that the various folding on of the line A on P create pieces which are tangent to one and the same parabola. The obtained parabola has a direct piece, the line L, and as a focus, the point P, or formulated otherwise, this parabola is the envelope of this piece. Rao does not use the term envelope, though it was well known during this time. And as you can see, a depiction of this process can be seen on the slide, how actually one obtains the shape of parabola from the various foldings of the line on that one. Now, Rao's depiction is presented in the following slide. Now, while it isn't outside the scope of this talk, it is important to underline that mathematical ideas do not appear out of nowhere. The question is therefore, how did Rao came to think about paper folding in terms of mathematics? This question has a quite interesting answer. Rao underlines at the introduction of his book several kindergarten activities and also notes playful objects and activities called self-equation, introduced at modern kindergarten by the 19th century pedagogue Friedman. That is one of the sources of Rao's inspiration to think of folding mathematically was exercises and ludic objects given to children at kindergartens. But how this transfer of knowledge occurred is a topic for another. To return to Rao's book, it became pretty influential. And the question is, why? That is, why do we even know of its existence since it was a book published by a non-European mathematician from India at the end of the 19th century? The answer is the following. 2 years after the publication of the book, Felix Klein, one of the famous mathematicians in Germany at the time, mentions Rao's book in his 1895 book, in German, Famous Problems of Elementary Geometry, a book which was translated to English in 1897 though it is not clear how Klein obtained Raw's book. Klein says the following: a Hindu mathematician, Sundara Rao, Madras, published a little book from multiple exercises in paper folding, in which this idea is considerably developed. The author shows how by paper folding we may construct by points such curves as the ellipse, etc. Klein's book was translated, as noted, in 1897 to English, and his remark has sparked an interest, causing a republication of Raw's book in the USA. In 1901, a new edition of Raw's book was published in Chicago, where the editors remarked that they were enthusiastic regarding the novel methods presented. Raw's book and its republication have caused a popularization of the mathematization of paper folding. And this popularization led other mathematicians to take paper folding seriously from a mathematical point of view. Which brings me to another example. An Italian mathematician was from 1927 a full professor at the University of Ferrara, where she taught until her retirement in 1950. While working mainly in the field of algebraic geometry, algebraic topology, and photogrammetry, between 1934 and 1936, she published several papers on the mathematics of paper. With the work of Bell, who was familiar with Raw's work due to Klein's citation, one of the famous problems of antiquity, constructing a segment whose length is the third root of 2, was solved only via paper folding. So, to recall briefly, folding a point on a line is equivalent to finding a tangent to a parabola, which is exactly what the Rowe showed us. Therefore, folding two different points on two different lines is equivalent to finding a common tangent to two parabolas, a construction which is always possible. Bellow's fundamental insight in 1934 is exactly a proof of the. So this is actually called Bellow's fold. Given 2 points, P1 and P2, and 2 lines, L1 and L2, one can make a single fold that places P1 onto L1 and P2 onto L2 simultaneously. Now, how does Bellow's construction lead to solve the problem of the multiplication of the cube, or more precisely, the problem of constructing a segment whose length is the third root? So here is Bellow's construction. She took the points A, -0, and 0, -2, and folded them onto the lines x = 1 and y = 2. She then proved that the intersection of the obtained increase, the dotted line in the slide, with the x-axis is, with the y-axis, is the point C, whose coordinates are 0 and the third. Now, needless to say, Bellow's 1934 constructions were a mathematical breakthrough, since she also showed that one can solve equations of degree 3 and 4 with paper folding, or more precisely, one can construct segments whose length is the solution of such equations. Recall, with straight edge and compass, one can only solve equations of degree 2, hence the importance of Bellow's results. However, Bellow's discoveries were completely forgotten. A simple explanation would be to say that during the 30s of the 20th century, when the construction of segments was not in the center of the mathematical interest, Bellow was certainly making an exception. However, other reasons, as well as a more sociological, historical explanation, should be deepened to the fact that till 1988, there was no reference for Bellow's finding. So what are actually the reasons for this? The first reason reflects how Bellot herself refers to her own results. Taking a look at the introduction to Bellot's selected works published in 1967, the two papers on geometry and paper folding that are mentioned in this volume are described to have a didactic origin. This might indicate that the method introduced in Bellot's paper was considered as belonging solely to the domain of mathematical pedagogy and not to the domain of research or pure mathematics. Indeed, after 1936, Bellot did not refer again to her own theorems on folding-based geometry until 1953, where she indeed combined her findings in her book on lectures on mathematics, which stemmed from her lectures for students. The second reason concerned the social and academic atmosphere in Italy during the 30s and 40s of the 20th century. First of all, Bellot, as a woman mathematician, was by all means belonging to a minority, and this certainly made it more difficult for her research to be well accepted as contributing to the mathematical research and not to be immediately categorized as pedagogical. Second, paper folding might have been considered as not interesting for more senior Italian mathematicians. Indeed, during the 20s and the 30s of the 20th century, it was algebraic geometry. It was considered as the queen of Italian mathematics. And this domain certainly not included instructions within Euclidean geometry. In that sense, Bellot's discovery came too late concerning the mathematical research with respect to construction of segments, but also ahead of her time, as the mathematical interest regarding folding only became well known starting from the 80s to the 20th century. However, the main reason why Bellot's research was not known outside of Italy was the rise of fascism in Italy in 1950. How fascism deprived mathematicians in Italy from the works of some of its major contributors, especially after the 1938 Russian laws, is outside the scope of this. However, as is clear from the works in the history of mathematics in Italy, the connections with the mathematical communities outside of Italy were heavily strained and damaged. Here is a citation from a recent account on the situation of the Italian mathematical community in this period. The economic, political, and intellectual autarky desired by the fascistic regime ended by justifying at an outer level the choice of isolation. Racial law broken out in 1938 and the shield's painful support of Italian mathematicians to this further wickedness of the regime only made these detachments deeper. Publishing hence in English or making contact with mathematicians outside of Italy might have been practically impossible. And when the connections, the second mathematical to the other mathematical communities outside Italy were reestablished after the Second World War, Bellot's writing on paper folding were forgotten for more than 50 years. So the question is, how do we even know of Bellot's results? And why do we even know today of paper geometry? It is due to the work of the mathematician Cohn. Therefore, the last data and the difference regarding and the mathematization. Posita was a Japanese-Italian mathematician and origami artist. Born in Japan, he traveled to Italy to study nuclear physics at the University of Padua and stayed in Italy for the rest of his life. Being an origami fan, he organized a conference entitled the First International Meeting of Origami Science and Technology, which took place during December 1989 at Ferrara, Italy. One of the achievements of this conference was the republication of Belot's papers, which has prompted their acceptance and recognition. At the same time, it brought to the fore mathematical traditions and cultures which were completely new, neither reflecting nor continuing the old ones. The question which I would like to raise is as follows: how Rosita came to hear about Belot's results? In 1987, Rosita, together with the Italian Origami Society, created an origami exhibition. It is here we see how these communities of mathematicians and of origami folders were interwoven, and how the community of origami folders influenced mathematicians and had access to mathematical knowledge. The exhibition, entitled La Luna di Carta di Capo, was held in Padua, and the convention was one of the first meetings of origami folders in Europe and Japan. However, Rosita, in his contribution to the catalog, does not mention any mathematical discoveries that paper folding may prompt, although several models of polyhedra were presented in the exhibition, as well as other models. It seems that Rosita was exposed to Belot's work through meetings with other colleagues from the Italian Origami Society, where it was also a member. Indeed, Rosita acknowledges these colleagues from the origami community in 1988 in an article published in a journal called Quadrato Mani, where he showed how one can solve any way paper folding, indicating that this method is based on Belot's method. Rosita then lists several reasons why Belot's papers were forgotten, noting that one of these reasons was that her papers were written in Italian, which did not have international slavery as self-said back then. It is a somewhat interesting remark, since Rosita himself published only in Italian until this point. Encouraged by these meetings and discoveries and by his attendance at the conference called Symmetry of Structure, Rosita decided to organize the first international meeting of origami science and technology. And although this conference was a success, followed by subsequent conferences, a tradition that continues until today, the main impact, mathematically speaking, of this conference was due to its proceedings in English, edited and published by Rosita himself. The influence, ramifications, and implications of these proceedings are beyond the scope of this talk, but to mention again, it is there that Belot's papers were republished. To slowly conclude my talk, I would like to present one example from these proceedings. This example consists of one of the modern approaches to folding-based geometry, axiomatization. In one of the papers in these proceedings, Rosita presents 6 basic operations of folding-based geometry for which, as he describes later, one does not any apparatus, but only the action fold the paper. These 6 operations are as follows. Now, I will not read all these operations. Let's just read the first and the last one. So the first one is given 6 points. You can fold, making the crease pass through both points. The last one is the most interesting one. Given 2 distinct points and 2 distinct lines, you can fold, superposing the first point onto the first line and the second point onto the second line at the same time. Now, none of these operations were revolutionary or new. Rao and Heller mentioned some of them as well. For example, the 6th operation, that is the last one, what just read, is the fold Belot herself first formulated in her papers, but listing All of these operations together was new. However, Kuzlita does not even try to prove that the list is complete, that is, that other operations which would be found or added to the list would in fact derive from the list operation. He also does not attempt to prove that the operations are independent of each other, or that one operation may, in extreme case, or in private case, lead to another operation. But the story of how these problematic issues were resolved and is a subject for now. Nevertheless, one can clearly say that with the 1989 influence, paper folding based geometry, though not replacing the compass, straight edge based geometry was saved from falling apart. Thank you very much.
Thank you very much. That was a very beautiful and enlightening talk, I think, not only for algebraic geometers. I have a remark, not a question. That, I mean, the Italian school of the 19th century, they put the foundation of the geometry part of algebraic geometry, was all written in Italian. And nevertheless, it made it to the international community slowly. So maybe the reason that she was forgotten because it's a she. So this is connect very well to the umbrella of this masses everywhere, that it's for raising the issue that women are not recognized enough, visible enough, and not numbered enough, etc. in mathematics. But this is really very nice, and it's nice that it was discovered. So maybe one day when you can physically come here, you can do our exhibition and exercise and competitions. Here we have another competition. We're going to have another competition. I will say it after the next talk. But we can have a competition of origami and folding paper. Anyhow, anybody has, and another remark. In the previous talk, June said that people say that women who do mathematics will have short life expectancy. But as I see from what you wrote, she lived more than 100 years. So that's,
she did.
it's a good counterexample. Okay, any questions? So I say the geometry, the geometry part of algebraic geometry grew up in Italy, and the algebraic part grew up in Germany. And I don't know, I mean, because you went to Germany after PhD and you spent so many years there. So maybe that's the influence that brought you. But this was very, very interesting. So if there are no other questions or remarks, we'll thank you. Sorry, go ahead.
I just do have a remark on what you said, Mina. I think obviously you have a point that I think most of the mathematicians at that time knew how to read Italian. But you're right, the point is that the subject of the research of paper folding based geometry was just marginal and at the same time marginalized due to several reasons. And one of them was that, well, Belloch was a woman, actually. So, yeah.
Yeah, maybe another remark. You mentioned, I think you said that some of the mathematicians were sort of support of the fascist. Some of the mathematicians.
Well, support is, it's a strong word. That is, all of the professors in Italy had to eventually sign a support letter of the fascist regime, and if they didn't sign, they would have. Yeah, and exactly, they would have been fired. So
there were many, but there were many Jewish mathematicians in Italy.
So obviously they were fired and eventually deported to some extent.
Some Italian mathematician told me that maybe that's the reason that the Italian mathematics declined, that the fascists, most of the very prominent algebraic geometers.
Indeed.
Okay, talk for many hours. Thank you very much for doing it in a late night hour. Thank you.
Thank you, Mino.